Welcome to lecture 4 of A Gentle Introduction to Fourier Analysis and Polytopes. My name is Sinai. I work at IME, University of Sao Paulo, and this is part of the 33rd Colóquio Brasileiro de Matemática. So let's see what we have for you today. Application of Poisson summation to the theta function. Finally, we have some nice applications of Poisson summation. Slightly more general, also Poisson summation for lattices, the convolution operation, bread and butter of the theory of Fourier transforms, and finally, and this is very beautiful, I think, Minkowski's geometry of numbers. And so we'll prove today Siegel's formula, and a consequence is Minkowski's first classical theorem in the geometry of numbers. First, the Poisson summation formula. And let's recall from the last lecture that we proved already this Poisson summation formula. If f is a Schwartz function, we have this Poisson summation formula. In particular, we also have the special symmetric case in the bottom here. And as we pointed out last lecture, they're equivalent. A classical application now that we like to do is that for the Jacobi theta function is to prove the functional equation of this theta function. So what is the theta function? This is a one-dimensional vanilla flavor, the most basic of all theta functions. And there are many of which hopefully we can get into in the future as well. And so the one-dimensional version is the sum of e to the minus pi t n squared over all integers n, and t is going to be positive for any fixed positive t, the variable here being t. There's also a way to extend t to the upper complex half plane, where it becomes a modular form relative to the action of SO2Z. But for us, for now, we can stay in the real domain for t. It has a very beautiful functional equation. Theta of 1 over t is square root of t theta of t. And this is the basis of a tremendous amount of number theory. In particular, for example, Riemann used this to prove the functional equation of the Riemann zeta function by taking the Mellin transform of this particular functional equation. So let's prove it using, the proof is basically a one-liner, so to speak, following the Poisson summation formula. So we proved using the, we defined these Gaussians in the last lecture, and we said that the Fourier transforms of the Gaussians are this. We left it as an exercise, but indeed it's one of the exercises in our book. And we recall the one-dimensional Poisson summation formula here, and this should be f of n. There's a small typo, summation over n integers, f of n. And so let's apply this Poisson summation formula to the function f of x equals g of x, where g is g sub t of x, where these are the Gaussians for any fixed positive t. And so because these Gaussians, so let's see, the Gaussian has the kind of the beauty of it is that the Fourier transform is essentially itself, and so it enjoys that property. And so here's the Fourier transform at the bottom of the Gaussians using this property that the Fourier transform is another Gaussian, and this by definition in the bottom is the theta function. So to recap, we have this so far using the first step is Poisson summation. The second step is the Fourier transform of the Gaussian, and the third step is the definition of the theta function. On the other hand, by definition of the Gaussians, the infinite sum is this infinite series, isn't it? It's the same as this infinite sum. And by definition, we have the theta function at 1 over t times 1 over square root of t. So these are just definitions. And so that's it. So theta of 1 over t is theta of t up to this square root of t factor, equating the end of the first line with the end of the second line above. And that's the functional equation. So really it's just a quick application of Poisson summation. This was known for well over 100 years, maybe close to 200. But in any case, yeah, as we said before, Riemann used this functional equation to prove his famous functional equation for the Riemann zeta function. Let's prove a slightly different Poisson summation formula. Again, for Schwartz functions, let L be any full rank lattice. Then we have this functional equation where the lattice on the left is the lattice we're given, and the lattice on the right is the dual lattice. And again, we have the symmetry. But we're being a little bit unfair, right? Because what is a full rank lattice? We haven't mentioned that. And what is the dual lattice? So we should talk about these things, to be fair. So let's go into a very brief, extremely brief introduction to lattices, but I think useful. So what is a lattice? It's defined as the integer linear span of a fixed number of linearly independent vectors, let's say v1 up to vm, in Euclidean d-dimensional space. Because they're linearly independent, necessarily m is less than or equal to d. And so we have, by definition, lattice is the integer linear span of v1, v2 up to vm. So let's write it down. And we notice that once we write it down, we can equivalently write it down in a matrix form. Namely, it's the matrix whose columns are the vectors v times an integer vector n1 up to n sub m, composed of integers. And so we can write it as m, the m of z to the m. In other words, we can write it as the image of the integer lattice under the matrix m. And this way of writing a lattice is a very, very common way to write it, and we'll keep using that throughout. And so let's see what we have. If m is equal to d, we call the lattice a full rank lattice. And so that's when the number of vectors is equal to the dimension. And in this case, we define the determinant of the lattice to be the determinant of the matrix M. So by definition, when you have a full rank lattice, the determinant is equal to the determinant of M. And that's called the determinant of the lattice. Let's see what we have next. And we're already familiar with the integer lattice, for example. It's just, again, the set of all vectors in Euclidean d-dimensional space such that all of the components are integers. And now we would like to, let's see, let me clear these drawings. We would like to have an example. Here's a two-dimensional integer lattice, which is a sublattice of the two-dimensional the usual two-dimensional integer lattice. These are called integral lattices, where they're sublattices of the usual integer lattice. And we can write it as the image of the integer lattice under M, where M is this 2x2 matrix. Why? Because as we see, this two-dimensional lattice composed of these dark green little balls, it has two basis vectors, namely 3, 1, and -2, 2. And so it's generated by these two integer vectors, the columns of the matrix M. And as we saw in the previous slide, these columns are the basis vectors of the lattice. And so we can write it in this form. Here, the determinant of the lattice is 8. And we can see that because that's the determinant of this 2x2 matrix. And so the determinant of the lattice is the absolute value of the determinant of the matrix, always, by definition. Okay, so that's the kind of a quick intro to lattices. We need one more piece of information at the moment about lattices, and in the future we'll get back to a much more detailed study of lattices, and as we do have in the book. Given a full rank lattice, L is equal to the image of the integer lattice under the matrix M, we also need the notion of its dual, defined by M inverse transpose of the integer lattice. So a full rank lattice by definition has a matrix M which is invertible. We take the inverse, we transpose it, we apply that to the integer lattice, and by definition that's the dual. We see immediately that the determinant of the dual lattice, by definition, it's the determinant of the defining matrix, which is determinant of M inverse transpose. By linear algebra, that's 1 over the determinant of M, and by definition, again, the determinant of M is the determinant of L, the original lattice. And so we immediately have this lemma that the determinant of the lattice times the determinant of the dual lattice is equal to 1, just by looking at this, the ladder line of equalities. And that's it. So that's a quick intro to lattices. And there's a lot more, obviously. There's a lot of current research involving lattices for lattice-based cryptography, for example, which is quite important. But in number theory, it's again, very, very beautiful part of number theory to study lattices, simply because, well, the integer lattice in the dimensions is a natural extension of the integers. Okay, here's again what we want to prove next, the Poisson summation formula for lattices. And now we understand what a lattice is. Now we understand what a dual lattice, so this makes sense. And so let's go for the proof. it'll follow quickly from two facts. One is from the Poisson summation formula that we already know, namely for the integer lattice, and two, the stretch lemma, which we studied already. Now, again, any lattice can be written as L is m of the integer lattice, where the determinant is by definition, the determinant of the lattice is by definition the absolute value of the determinant of m. And now using our Poisson summation formula that we already know for the integer lattice, let's see what that says. Well, we can rewrite this infinite series of f of n as the infinite series of f composed with m of k. Well, why? Because by definition, when n runs through the lattice, that means n runs through m of an integer vector. So we set n is equal to m times k. So let me annotate here for you. When we set n is equal to m times k, n runs through the lattice, and k runs through the integer lattice. And so as k runs through the integer lattice, n runs through the lattice. And using this change of variable, we have this the line here that we wrote next. And now we can continue. Let's see. Now we use Poisson summation just for the usual integer lattice. So that's this next step, the usual Poisson summation that we already had before. And now we use, you see, we have the Fourier transform of f composed with a linear transformation. And that's beautiful because we already know what that is. That's the stretch lemma. So to recap, let's see what we have so far. We have the first step is the usual definition of the lattice. The second equality we already had before in the last slide. That was the usual Poisson summation formula. And the next step is the stretch lemma that says that the Fourier transform of f composed with a linear transformation m, invertible m, is given by that formula. We already proved that before. And the last step is, again, using the definition of the dual lattice. So by definition, as xi varies over the integer lattice here, m inverse transpose xi, as we saw before in the definition of the dual lattice, that varies over the dual lattice. Where by definition, the dual lattice is m inverse transpose applied to the integer lattice. And that's it. That is the proof of the Poisson summation formula for lattices. So obviously not too difficult. So this is what we proved so far, extremely useful. And in the future, we can even have a further Poisson summation formula where we relax the hypothesis. Instead of assuming it's a Schwartz function, we can assume that it satisfies some more lax hypotheses on the rate of the decay at infinity. For now, let's go on and study convolutions, again, part of the theory. Suppose we have two functions f and g, L1, in other words, absolutely integrable. We define the convolution by this integral. And this integral, very interestingly, is kind of the way waves like to multiply. Why do I say that? Because of this following lemma. So this is called, we'll call this the convolution lemma, that the Fourier transform of the convolution is equal to the product of the individual Fourier transforms of f and g. And so on the space domain, if you like, we have the product on the right, a function, let's call it f hat, times the usual multiplication of functions times g hat, where on the left, we have f convolved with g, and then the hat of that. But you can imagine taking the hat again of this identity. In other words, you can apply the Fourier transform again to both sides, and then you'll have f convolved with g is the Fourier transform of f hat times g hat. And so we see that you can start with f convolved with g on a space domain and end up with, you can start with a function times another function in a space domain, and then we take the Fourier transform in a frequency domain, you end up with the convolution. And so it's very natural. The Fourier transform takes multiplication to convolution. Very interesting phenomena. And convolutions are kind of wonderful because they satisfy a nice many algebraic properties. So in fact, they form an algebra without identity, sadly, but we can get into that another time. So, but they allow us to smooth any function by convolving it with another function, or even by convolving it with itself. just to mention this new multiplication of convolution, it does give the L1 space the structure of what's called the Banach algebra. We won't get into it, but it's quite important. And so now the L1 space, before, it didn't seem to have structure, but with this operation, all of a sudden, it becomes a whole new creature, an algebra, which is very interesting. Let's see some examples in one dimension. Here's the indicative function of the symmetric interval between -½ and 1/2. We already mentioned before that the Fourier transform is this sinc function. And we already proved that the Fourier transform is always an entire function. It's infinitely smooth, right? The Fourier transform of any polytope, the indicative function of polytope, is infinitely smooth, as we already proved. In this case, the function we start with decays very rapidly. It decays in the best possible sense, in a sense, because it's zero identically outside the interval. So engineers call this the perfect filter. But on the Fourier transform side, we have the sinc function, which is by definition sine pi xc over pi xc, infinitely smooth. It has zeros at all the integers except at 0. And the value of the function, the Fourier transform at 0, as we see, it's 1. It happens to be, as we know, the volume of the polytope, which is in this case 1 as well. Let's see. Let's superimpose onto this what happens when we take the convolution with itself. So having now learned about the convolution, the definition anyway, this is nice because it allows us to, let's do it again, to convolve the function with itself. So when we convolve the indicator function of the interval with itself, we get this triangle function. Sometimes this is called the hat function. And it's a very nice continuous function. It's not differentiable, obviously, at -1, 1, and 0. However, it's already much smoother than the indicator function was. By the convolution lemma, the Fourier transform of the convolution is the product of the transforms. So we get this picture below. The Fourier transform of the function above is the function below, which is the square of the sinc function. So it's a square of sine pi xc over pi xc. And as we can see already, looking at the graph below, which is very pretty, it decays much faster towards infinity than did the original sinc function. So if we superimpose onto the picture below the original sinc function, you can see that the original sinc function decays, but the function, which is the Fourier transform of the convolution, decays faster. All right, so we already see some very new, interesting phenomena. First, the convolution of the indicator function with itself is already smoother. And next, the Fourier transform decays faster. And so you might conjecture that this persists forever. And in fact, it does. It's a theorem. Well, if we don't get back to it in lectures, it's certainly in our book. And the smoother the function becomes, the faster its Fourier transform decays to 0 as we go to infinity. And that persists. And so we'll get back to this hopefully in another lecture. And we'd like to see now some geometric applications, geometry of numbers. So very exciting geometry of numbers. And one of my favorite things. And here's Minkowski saying, opa, verdade. So let's see. The basic question, or one of the basic questions, there are many, is how large does a convex body have to be in order to contain a non-zero integer point? Although this question may sound innocent, it has just so many consequences that are important that it's hard to fathom. The existence of an integer point, you can kind of smell the number theory here, but it has many, many consequences. For example, one consequence is the Fermat theorem of the sum of squares. One can use this to prove that every prime that's 1 mod 4 is a sum of 2 squares, but by just proving the existence of an integer point in some convex body. So first, we should be fair. What is convex? What is a body? So let's define it. A body is defined as a closed bounded subset of Euclidean space. A set is called convex if for any 2 points xy in the set, the whole closed line segment connecting them again lies in the set. So that's a convex set. We begin now the study of are relationships between convex body and the integer lattice. So now that's basically the heart of this Minkowski geometry of numbers, the relationship between convex body and lattices. And so let's see what we mean by that. Suppose we start with a two-dimensional integer lattice. So these are the points here below. And the center is the origin. And we have some convex body here sitting and containing the origin. Let's expand it. And let's see when we catch an integer point. So, here we see one integer point already. Here's another one on the left. And so we caught at least one non-zero integer point in the interior of this convex body. We note that the area of this convex body is greater than 4. If we go back, the area of this one is less than 4. And so it is a theorem of Minkowski that for convex bodies that are symmetric, very symmetric about the origin, and we need to define what that means. If the area is less than 4, they will not contain another integer point, no matter how hard we try, as long as they're convex and symmetric about the origin. But if the area is larger than 4, then they always will. So let's see. It's always good to ask what could go wrong, even if we do make these assumptions. Well, let's look at this picture. The volume of such a convex body, we can stretch it out to approach infinity, and so we can make this volume as large as we want and still not contain any integer points, because we're lying between these two vertical lines that contain integer points. And so it seems like this would contradict things, but all it tells us that we have to be a little bit careful how we position our body if we want to have an interesting result. And so one natural way to position it to assume something about your convex body is to assume that it's symmetric about the origin. And so what does that mean? That just means that for every x in B, minus x is in B, for any x in Euclidean space. And so that means, by definition, that the body B is symmetric about the origin. In particular, it contains the origin. And for every x in the body, minus x is in the body. And so this symmetry about the origin plays a major role in the geometry of numbers. Here's Minkowski's first theorem. Let B a body in Euclidean space. And again, by a body, we mean compact, in other words, closed and bounded. Let it be a d-dimensional convex body, symmetric about the origin. Now, if the volume is bigger than 2 to the d, then it must always contain a non-zero integer point in its interior. And so innocent as it sounds, it's a very powerful result. Discovered by Minkowski, I think around 1880, 1890, maybe published officially a little bit later, but around that time. And this classical and extremely useful in many fields result of Minkowski will follow as a corollary of Siegel's formula, which we prove next. And by the way, Minkowski did much more than this. This was just his first theorem. He went on to prove incredible consequences of this and generalizations and extensions. And by the way, Einstein was one of his students. And as we mentioned before, I think Minkowski was fond of saying that Einstein slept in his classes. But in any case, Siegel's formula is our first relationship it's our first relation between the Fourier transform of a convex body and the number of integer points it contains. Here's Siegel's formula, of which a quick corollary will be Minkowski's theorem. Let's see what it says. Let B be a d-dimensional convex body, again, symmetric about the origin. If the only integer point in the interior of B is the origin, then we have this identity, a wonderful, kind of incredible identity, really. It's true for all bodies B in any dimension, symmetric convex about the origin bodies. And it's a fantastic identity. If only we can compute the Fourier transform of B, maybe we can do some more things with it. When B is a polytope, in fact, we want to. So in any case, before we prove the Siegel's formula, we need to understand a little bit more about Minkowski sums. Let's define what a Minkowski sum is. Given two bodies A and B, the Minkowski sum is the set of all A plus B, such that little a is in the body A and little b is in the body B. Seems innocent enough, but in fact, this innocent-looking definition captures a lot of information. For example, if we have a square and we take the Minkowski sum with this little disk, this little ball in 2 dimensions, we have this figure here. You can imagine taking the center of the little disk and placing it around each point of the boundary of the square. So it kind of moves around until we get this figure. The union of all the points in this figure is the Minkowski sum. And so it's kind of a smooth version of the square, if you like. This is very common in image processing, machine learning, and so on, computer vision as well. So similarly, for any set K in Euclidean space, the Minkowski symmetrized body is the following set, which will come up in the proof of Siegel's formula. We take 1/2 K minus 1/2 K. It's like the Minkowski sum, except with a minus sign. And by definition, it's 1/2 X minus 1/2 Y, where X and Y vary over all points in K. Again, innocent looking definition, but with tremendous consequences. So this is, by the way, this is one of many ways to symmetrize a body. There's the very well-known Steiner symmetrization, which we won't get into, but just to let you know, there are many ways to symmetrize bodies, and starting with either a convex body or sometimes even more general bodies, there are many ways to symmetrize. This way of symmetrizing is called the Minkowski symmetrized body, but we'll just call it a symmetrized body. And we have the very nice fact, very easy fact, in fact, that a body B is symmetric about the origin, if and only if B is equal to 1/2 B minus 1/2 B. So this equality is equivalent to B being symmetric about the origin. Okay, so that's it for now for Minkowski sums. Let's go on and finally prove Siegel's formula. Again, this is what it, just to recall, this is again what it said. We have this identity, assuming that the only integer point in the body B is the origin. And also assuming, of course, that the body B is convex and symmetric about the origin. So without further ado, let's prove Siegel's formula. This proof will use Poisson summation. Siegel's original proof used Parseval, which we didn't mention yet, but another basic ingredient in Fourier analysis. But starting with this convolution, which we now know, so let f of x be the indicator function of 1/2 the body B, which is a dilation of the body B. You shrink the body B by a factor of a half, convolved with the indicator function of negative 1/2 B. So again, negative 1/2 B is, you just take every point in B and multiply it by negative a half. It's another dilation. So if you take the convolution of these two functions, we plug this function f of x into Poisson summation. The fact that this convolution is continuous is an exercise. Let's plug it into Poisson summation. Let's see what we get. For the left-hand sum, we first get the following. Well, by definition, this integral is f of x, because that is the convolution definition of these two functions. So we take the first function, the indicator function of 1/2 b. The convolution of that with the indicator function of negative 1/2 b is this integral. We plug it into Poisson summation. And we want to take, of course, now the Fourier transform of the summand to really apply Poisson summation. So far, this is the definition of f of n. And using indicator functions, we just stare at this integral for the moment, and we notice that y must be in 1/2 b, and n minus y must be in minus 1/2 b. So we wrote this on the bottom here, but both of them together imply that n must be in y plus minus 1/2 b. In other words, n must be in 1/2 b minus 1/2 b. Just to review a little bit, to go a little bit slower for us, let's see. So this identity here below, n minus y in 1/2 b, this implies that n is in y minus 1/2 b, just by taking y to the other side. But on the other hand, we're assuming y itself is in 1/2 b. So this is y is in 1/2 b. And so if we just write this again, we see that n is in 1/2 b minus 1/2 b. Technically, I put a subset here. Okay, so there you have it. N is an element of 1/2 b minus 1/2 b. But we know B is symmetric, it's a symmetric set, and we know by that exercise that we had that for a symmetric convex body, symmetric about the origin, 1/2 B minus 1/2 B is equal to B. And therefore, we can continue to say that, as we mentioned just now, that this line, because n is in B, we have this line from before, and we know that n is in B. Okay, so let's see what's next. By hypothesis, though, the only integer point n that belongs to the interior of B is the origin. And so we see that n is in B, but n has to be the origin because those are the only integer points in B. And so, n is in the origin, n is the origin, and therefore in this integral we plug in n equals 0, and we get this line on the bottom. So now we have this. Oh, there's a typo here again, of course, but it's a small typo that we have the sum, of course. Oh no, no typo. Okay, right. N is 0, so the infinite series over n only has one term. Right. Very good. And so this whole infinite sum of integrals just become one term, the integral with n equals 0. So that's nice. And so the whole left-hand side reduces to just this one term. Now we notice that these indicator functions are really identical because B is symmetric about the origin. Let's see how that works. So we recapped from the last line. But because B is symmetric about the origin, the indicator function of minus 1/2 B at negative y is equal to the indicator function of 1/2 B at y. And so we can just multiply these together. They're the same. So the indicator function of a set squared is the indicator function of the set. And so we have just this integral over the indicator function. And now this is just the integral of 1 over 1/2 B, which is the volume of 1/2 B. And so that's very nice. The whole left-hand side of Poisson summation, we didn't compute transforms yet, just reducing the left-hand side using the definition of F reduces to the volume of 1/2 B. Using elementary considerations of volumes, just the integral definition, you can see that the volume of 1/2 the body is the volume of the body times 1/2 raised to the d power in dimension d. And so the whole left-hand side of Poisson summation reduces to the volume of B divided by 2 to the d. And so that's 1/2 of Poisson summation, literally the left half. Onto the right half, usually the more interesting part with the transforms. So the Fourier transform of little f, by definition, is the Fourier transform of this convolution, which was little f. And we know by the convolution lemma that it's the product of the transforms, okay? And now we write the definition of the transforms. So the first transform is this integral. The second transform is this integral because we have the indicator functions. And so integrate over 1/2 B because of the indicator function. For the second one, we integrate over negative 1/2 B. And now we use the fact that B is symmetric. So negative 1/2 B is the same as 1/2 B. And so we put that in. But in order to make this change of variable, we have to be a little careful. There's a minus sign that goes into the x. So as x varies to negative 1/2 B, we make a change of variable. And so there's an extra minus sign that appears there, minus c, or if you like, minus x. And so now these integrals are almost identical, except one is the complex conjugate of the other. And so we take the minus sign above, we can put a complex conjugate above the e to the 2 pi I, and then we take the conjugate yet one more level above. The conjugate of the integral is just the integral of the conjugate integrand. And so we have this line, and of course, the integral times its conjugate is the norm squared, the absolute value, the norm squared in terms of complex numbers of the integral, and that's just this second line. And so now we're going to do something a little bit interesting, very common in this business. We take out the zero term. As we know, when we value the Fourier transform at 0, we're going to get the volume of the object. We take out the zero term. This will give us some volume, and we leave the rest intact. So let's see the zero term. Let's work it out. Again, we know that the Fourier transform of 1/2 B at 0 is the volume of 1/2 B. Now we have to square it. And so we get finally that the right-hand side of Poisson summation on the bottom here in red is the volume of B squared, this time divided by 4 to the d because it's 1/2 to the d, but now we square it. So it's 1/2 to the d squared, which is 1/4 to the d. And now we add this, of course, the sum of that Poisson summation gave us of all of these other terms. Work C varies over the whole lattice except the 0 term, which we pulled out. And amazingly, that's essentially it. That's the proof essentially of the formula of Siegel. So let's wrap up, see what we have. Just to recap, here's Poisson summation for the lattices. The left part gave us the volume of B over 2 to the D. We had that computation on the first slide. The second part gave us this right-hand side, and that's it. Now we multiply both sides by 4 to the D over the volume of B, and that's the formula of Siegel. And so we've derived the famous Siegel formula for convex bodies symmetric about the origin using nothing more than one of our favorite tools, Poisson summation. And so here's what we proved again. For any convex body, B, symmetric about the origin, assuming the only integer point in the interior of the body is the origin, we have this beautiful formula. If only we could somehow compute the Fourier transform of the indicative function of the body, then we would be in business. So amazingly, nobody has done that yet. So I encourage you to try doing something like that in the future. And finally, let's prove Minkowski's first fundamental theorem. Sometimes it's called as a quick corollary. What does it say again? Let me remind you what it said before. Let B be a d-dimensional convex body symmetric about the origin. The same hypothesis as Siegel's formula. If the volume of B is bigger than 2 to the D, then B must contain a non-zero integer point in its interior. Proof. Let's prove the contrapositive. Let's prove the contrapositive where we therefore have to assume that B only contains the origin and interior. That's the negation of this conclusion up above. And then we have to prove, of course, that the volume of B would be less than or equal to 2 to the D. Well, let's just stare at Siegel's formula for a moment. If we assume that B only contains the origin and its interior, that was exactly what Siegel's formula wanted to assume. And then Siegel's formula guaranteed using this assumption that we have that formula. But notice that all of these terms in this infinite series are positive or 0. They're non-negative, in other words. And so the volume of B must be at most 2 to the D. So that's it. That's the proof of Minkowski's first theorem. Wonderful. All this, very beautiful how all this theory ties together in a very, very tight story that has many repercussions. And so that's it for today. Here are chapter 4 exercises for you to grind your teeth on, and from our book with IMPA. And that's it. So as always, stay curious, ask questions, and a te breve.